At COCOWATT, we have received so many requests from our community to cover CAN communication on AURIX. And we hear you. That's why we are thrilled to welcome you to this deep dive into the MultiCAN Plus module of the Infineon AURIX TC275 microcontroller. In this video, we will explore how this powerful CAN controller enables robust, high-performance communication in modern automotive system. Welcome to COCOWATT again. Here is what we will unpack today. First, the basics of CAN, including frame formats, bit timing, and error handling. Then we will focus on the MultiCAN Plus feature unique to AURIX TC275. 256 message objects, full CAN with basic CAN, and advanced filtering. We will walk through step-by-step firmware configuration, explain the transmit and receive flow, and finally run and interpret a live loopback demo. This is not just theory, it's practical production-grade knowledge you can apply directly. AURIX architecture, GPIO, VADC, DS-ADC, GTM, and more. Subscribe to COCOWATT and find the complete AURIX playlist in the description below, so you never miss a deep dive. So let us start. Let us explore the essential of the CAN controller area network, focusing on its timing, errors, and module times. Starting with basics, CAN is an asynchronous serial bus where nodes are connected in a linear or wired AND structure. This allows for efficient communication across devices. One important aspect is the bus logic, a dominant bit represented by 0 and a recessive bit represented by 1. The maximum speed of CAN is 1 megabit per second in classical CAN. But remember, as the bus length increases, the speed must decrease to maintain reliable communication. Data coding CAN uses NRC with bit stuffing to ensure synchronization, which means no more than 5 consecutive bits of the same polarity. Also, in CAN arbitration, the lower the ID, the higher the priority, allowing that node to win the arbitration. In terms of frame formats, we have classical CAN with 11-bit or 29-bit identifiers and CAN-FT, which supports dual-bit traits with the same bit lengths. When it comes to frame types, there are 4 to remember: data frame for transferring data, remote frame for requesting data, the error frame for detecting bus errors, and the overload frame for handling overload conditions. Finally, let us touch on the physical aspects. The CAN bus uses 2 lines, CANH and CANL, with termination resistance of 120 ohm resistance. If we come to CAN timings, let us start with nominal bit timing, which is essential for ensuring smooth communication among CAN nodes. Each bit is divided into 4 segments, which time quanta or TQ being the basic timing unit. Notably, the sync segment is crucial for synchronization, while the probe segment compensates for signal delays. The phase segment 1 and the phase segment 2 further refine timing by correcting edge phase errors, with the sampling point marking the end of phase segment 1. Overall, the total TQ per bit ranges from 8 to 25. Moving on to CAN-FD bit timing, we see a differentiation between the arbitration and data phases switched by the BRS bit. Error detection mechanisms play a vital role in maintaining CAN bus integrity. They include the CRC error, acknowledge error, form error, bit error, and step error. Each of these errors is addressed by specific responses, such as a retransmission in the case of CRC error. Let us also touch on the 3 errors: error active, error passive, and bus off, each indicating a different level of connectivity and error handling capability. Lastly, understanding module types is essential. Basic CAN handles only bit streams with the CPU managing messages, whereas full CAN or multi-CAN plus incorporates the full protocol in hardware, significantly reducing CPU load and managing high bus loads efficiently. 898 and Bosch CAN-SPEC version 2.0b and CAN-FT. The module which we are discussing includes one module with 4 nodes and offers an impressive 256 message objects. This can be individually allocated for both transmission and reception and include features like timestamping, and remote monitoring. The advanced acceptance filtering is particularly noteworthy, providing mask per message object and priority-based TX and RX. Node features include analyzer, loopback nodes, and timeout detection, programmable transmission delays. These functionalities enhance the module's adaptability and robustness. Interrupt handling is quite sophisticated with nodes and message interrupts, 16 output lines, and 256 notification bits. This ensures responsive and efficient communication. Lastly, the module includes clock and timing features with runtime jitter calibration and energy-saving capabilities like CPU ideal mode and periodic message transmission without CPU intervention. It's highly AUTOSAR optimized, ensuring backward compatibility. MultiCAN module is designed to efficiently manage CAN communication, ensuring both flexibility and high performance. Within each CAN node, there is a bitstream processor. This is the workhorse for handling frames, whether they are data, remote, error, or overload frames. It manages crucial tasks like CRC checks, start of frame, and end of frame, as well as frame transmission and reception. Bit timing unit. This component is all about precision. It sets the bit length, determines the sample point, and handles synchronization and resynchronization process, ensuring the timing is just right. Error handling unit. It keeps track of errors by managing transmit and receive error counters, and it helps transition through error states such as error active, error passive, and burst of states, which we saw already. Additionally, the node control unit plays a critical role by enabling or disabling nodes, managing interrupts, and managing frame counters and timers. This ensures each node operates smoothly and can respond to events efficiently. Moreover, the interrupt controller unit is responsible for generating node-specific interrupts essential for managing real-time communication. Finally, the message controller and list controller are in charge of message handling, including allocation and delocation of message objects, which facilitates seamless CAN node exchange, FIFO operations, and gateway functions. Clock control for the MultiCAN Plus module. The FCAN is a timer clock responsible for CAN node operations like bit timing and setting the baud rate. This is crucial for ensuring accurate data transmission across the network. Next, we have FCLC, the module control clock. It is vital for things like register access and configuring the module settings. Think of it as the clock that keeps everything synchronized and running smoothly. In terms of clock sources, we have two primary types: the asynchronous high precision clock FA and the synchronous clock fsync_can, which is identical to FSPB. This offers flexibility depending on the needs of the system. The fractional divider plays a pivotal role here. It generates FCAN from FA by selecting every nth clock pulse. However, be cautious when using it at high baud rates due to potential jitter issues. Finally, let us touch on the lower power mode. If FSPB is reduced, the system switches fsync_can and FCLC to FCAN. It is important to note that FCAN remains identical across all CAN nodes and the baud rate is determined by FCAN alongside bit timing parameters. Message acceptance filtering in MultiCAN Plus. Firstly, we have received acceptance filtering for RX filtering. This process determines which message object will store a received CAN frame. The key criteria for acceptance include allocation to the CAN node list and matching the message status like MSG value and RX enable and direction. These conditions ensure that only the relevant frames are processed, priority is given to higher priority classes, and if priorities are equal, the list order is used as a tiebreaker. Next, let us talk about transmit acceptance filtering or TX filtering. This determines which message object is sent when multiple requests are present. Similar to RX filtering, this message must allocate to the CAN node list and have specific statuses like message value, TX request, TX enable 0 and TX enable 1. Here, priority plays a crucial role. Only the highest priority object is transmitted first. For equal priorities, CAN arbitration rules or list order come into play. Throughout both filtering process, the goal is to ensure efficient message handling and prioritization in the MultiCAN Plus system. Understanding these filtering criteria is essential for optimizing communication within the network. Let us explore the receiving object handling in detail. The message value parameter. It is important to remember that a message object can store only if message value is set to 1. If it is not, no data will be saved. RT select bit also another important parameter. This disconnects the message object from the ongoing frame reception, ensuring only the current context is stored. This is particularly useful for maintaining data integrity. Then we have RX enable, which enables the message object for reception. If RX enable is cleared, the reception is softly phased out, preventing any abrupt disruptions. Now let us talk about status indicators: RS updater, new data, and message lost. RS update shows the frame update is in progress. New data indicates when a new frame has been stored. Message lost warns us data loss if new data is already set. This is critical alert for maintaining data accuracy. Finally, when reconfiguring a message object, the steps are straightforward: clear message file, reconfigure the object, then clear RT cell and set message value again. Now let us explore transmit object handling in detail. In transmit object handling, the combination of message value, TX request, TX enable 0, TX enable 1 is essential for transmitting a frame. Each of these must be correctly set. Message value enables the message object, while TXRQ triggers the transmission request. Next, TX enable 0. It is particularly interesting. It allows us to temporarily suppress a frame up during updates. This provides flexibility and control over the transmission process. Finally, RT select ensures that transmission occurs only if the current context is valid, preventing errors and maintaining data integrity. The reconfiguration process is straightforward: clear message value, reconfigure the object, then clear RT cell and set message value again. This ensures that the message object is effectively reset and ready for new data. So next, we will explore the initialization steps for MultiCAN Plus in TC275 controller. We have divided the MultiCAN Plus initialization into 5 major main parts. The first one is global module setup. We begin by configuring the clock domain and fractional divider. See, the exact code I have given in the bottom of this each steps. You can follow this. This is what exactly we want to implement in our demo. It is critical to disable and then re-enable the anti-net protection during this process. So these are the steps: disable anti-net, enable the module clock, set the hardware sync barrier, configure the fractional divider to 100 MHz, select clock frequency async _ CAN clock source, and finally re-enable the anti-net protection. Node configuration. We have node 0 set as the transmitter and node 1 as the receiver. Enabling BM equal to 1 allows for an internal loopback. This is for internal loopback. For both nodes, after entering config mode, connect to the internal CAN bus, set baud rate to 500 kbps and ensure a sampling point of 80%. Timing for synchronization must be identical. Message object allocation. We assign message objects to nodes. MO0 goes to node 0's list and MO1 to node 1's. Now, message object setup. For transmission, node 0 will use a standard ID of 0FF and an 8-byte payload. Node 1 will match this TX ID and have interrupts enabled. Steps include validating the message object and setting the data length and enabling the RS interrupt. Finally, activation and transmission. Finally, we start the nodes and trigger the transmission, enable interrupts linked to ISR to the vector, turn on global interrupts and clear init and CC to start the node 0 and node 1. Load the payload, set new data and takes RQ to begin transmission. These steps ensure a robust setup of MultiCAN Plus system. We saw the code in detail. Now let us flash our code to our TC275 baud. Now this is the time for demo. We have what we are doing actually. We have node 0 acting as our transmitter or TS. It is sending a CAN message to node 1, our receiver of RX, using what is called loopback mode. This means the message is sent internally, allowing us to verify the transmission process within the system itself. Now here is a sequence what we are doing exactly. Once node 0 sends a message, a TX interrupt is triggered, which results in LED 1 lighting up. This signals a successful transmission. Let us see how this works. You can see the LED is blinking. So this is a successful transmission. Thanks for watching our video. If you have any doubts, please ask your questions in the comment section. Please don't forget to subscribe our channel for more exciting videos. Thank you so much.